Hey guys, welcome back. Day 46, last lecture. Talk about kinetic molecular theory for gases. So, as you can see, kinetic molecular theory, the motion of the molecules. 5 points, gas molecules are in constant random rapid motion, and they continually collide with each other in the walls of the container, surfaces, all that. We're assuming that there is no loss of energy. There are 100% elastic collisions. Gas molecules are very far apart compared to their size, and the attraction between the gas molecules is weak and ineffective, and the average kinetic energy of all gas molecules depends only on and is proportional to the absolute temperature of the particle. So the average kinetic energy is equal to 3/2 RT. So there's your temperature. And that derivation is beyond the scope of the book. The book even says so. Within any gas, there's a distribution of molecular speeds. Some are fast, others are slow. And here's an example of this. If we talk about like averages and whatnot, when we talk about bigger and bigger numbers, there start to become averages. And so there is, if I look up the street right here, there's a McDonald's right next to the college. Not everybody that drives by that McDonald's goes to that McDonald's. However, enough people go to that McDonald's that there's always people at the McDonald's. There's not too far from here, there's a couple Chick-fil-A's. They're always busy, except on Sunday. They're always busy, and people are always going to Chick-fil-A. I rarely go to Chick-fil-A. I rarely go to McDonald's. I rarely go to a lot of these places. That's because I have a dietary issue, not because I don't like Chick-fil-A. I just can't eat most of the stuff there. So, with the law of averages, just like if you have 5 friends, what's the chances that today is one of their birthdays? Could happen. But if you have 5,000 friends, today is somebody's birthday, and tomorrow is somebody's birthday, right? That's just because of the law of averages. And so when we look at this, right, if we look at the red graph here, so the relative number of molecules, and then the velocity. So if you look slow to fast, and these things do move pretty fast. And so slow, if you take the area underneath the red curve, is the same, that represents the total number of molecules, as the area underneath the green curve. And what that happens is your average temperature for red is right there, for green is right there. All right, so we just look at the difference of speeds. Now there's a root mean square speed, and this is kind of different because it goes into more of the stuff we're not really going to worry about in Chem 1. But think about this. When the gas molecules are traveling, and they're traveling, let's just say 500 meters per second, 1,000 meters per second, that's pretty fast, right? That's really fast. So 500, there's basically a little bit more than double is the miles an hour. So that's a little over 1,000 miles an hour. That's a little over 2,000 miles an hour. That's how fast these molecules are going in the room that you're sitting in. They're not going slow. However, they're so small, and they keep constantly hitting something and changing direction. So it might take them an hour to go across the room, even though they're moving at 1,000 miles an hour. Because they have to travel, thousands of miles, basically go across the room, because they go how they go, up, down, left, right, back, forth. Okay. Now, one of the things with this I want to point out, this formula, 3RT, or constant, M is the molar mass. So the heavier the molecule, slower at the same temperature. So if we look at particles, there's 2 takeaways I want you to get from this. One is that in a sample of matter, not every particle of that matter has the same temperature or the same amount of thermal energy. There's a distribution in there, right? Not everyone has the same. There's an average, right? And you think about a gram of water, there is 6 times 10 to the 22nd water molecules in that gram of water, right? That's an enormous amount of numbers, right? We just said if there's 5,000 friends you had, somebody's birthday's today, right? Just think about how many, that's 5 times 10 to the third. We're talking about 6 times 10 to the 23rd, right? Molecules. So there's a lot of molecular speeds, and there's a whole distribution. Some don't even look like they should fit in there, and that's okay. But that's the reality of the situation, that there's a huge distribution, and that the thermal energy of each of these molecules is not the same, even though there's a temperature of the average. The second takeaway is that I want you guys to know that heavier molecules move more slowly than lighter molecules at the same temperature. All right, so here's another example. You got O2, which is less than 500 molecular meters per second at this temperature, versus hydrogen at over 3 times as fast on average. Some are going as fast as 3,000 meters per second. Now, some are still going really, really slow. Again, that's a huge distribution. But as their speeds go up, you're looking at these. That's our measurements. The top here. All right, that's our measurements. The speed's going up on average, right? On average. So when we talk about gases and how they travel, let's talk about Graham's law, diffusion, and effusion. Diffusion is the movement of gas to uniformly fill any available space. So this is how gases spread out, right? And a liquid example of this is if you put cream into coffee without stirring it. You can see the cream start to fill into the coffee. All right. So diffusion is just how gases uniformly fill any space, which is nice, because if you don't walk into a room and wonder where all the oxygen's hanging out, it's evenly dispersed in the room. It's not all on the right-hand side or something like that. Effusion is moving a gas to a small hole or porous solid, so how fast gases go through. And you notice this with, let's say, a helium balloon. You get one of those helium balloons that say happy birthday or congratulations or whatever they are, and it's floating. And then after a couple of days, it's not floating as much, and it's not quite as firm as it was. But it's not leaking. What's happening? Gas is effusing through the balloon. The helium atoms are going through the balloon, right? You can do this with a balloon at home. If you take a balloon that you would blow up, before you blow it up, put in a drop of vanilla in that balloon. Blow up the balloon, right? You can see the vanilla inside. You'll be able to smell the vanilla through the balloon. And vanilla is much bigger than helium. But the balloon's not leaking, so to speak, right? But you've noticed this. Balloons will definitely do this. Gases will effuse. And so what happens is the rate of gas A compared to the rate of gas B, if we know the rate, right, their molar masses are different, or opposite. So the molar mass of B and molar mass of A, square root. And that's just how we know gases effuse. So if I know methane's, let's say CH4's gas rate, and there's methane's molar mass, I can figure out oxygen's rate because I can know oxygen's molar mass. I can do that. Works out. Okay. Now, this is the big thing. This is PV equals nRT. PV nRT. All right, so the pressure, observed pressure, A, is the correction for intermolecular forces, which is the next chapter in this textbook. It's usually one of the beginning chapters of Chem 2. N, number of moles, V is the volume squared. V, the observed volume, correction for particle volume. That B is a constant, and N is the number of moles. So the observed pressure is smaller than the ideal pressure because molecules hold each other back. So there is an attraction between molecules. So water likes itself a lot. And so even in the gas phase, there's an attraction between water molecules. The observed volume is larger than ideal volume because molecules occupy the same space, right? So they actually do, there's actually a little bit bigger. A is more important than B, especially if there's high intermolecular forces, which again is the next topic. That, ladies and gentlemen, concludes Chem 1.